Thank you so much. I'm so happy to be here in person. I gave a talk by video last year. It's not the same. I really love being here. So today, this evening, I'm going to talk about Vello, which is a project to do very high performance 2D graphics in Rust. So I'm going to be talking about the imaging model, the kinds of graphics that we draw, some of the goals behind the project. That a focus of the one of the goals is to take as much work off of the CPU and move it to the GPU. And that has a lot of challenges. You need to do a very efficient encoding of the graphics data that will be rendered. And then you need clever algorithms on the GPU to process that. And this whole thing is designed for very highly dynamic scenes. So, it doesn't rely on pre-computation. And then a very important part of the way that the engine is written is that it's in WebGPU. And so that leverages a lot of really good implementation work for both native and web. And I think one of the things that really makes me excited, and I'll show a little bit of a demo, is interop with other applications that are written for WebGPU and use WGPU as the implementation. So why would you do this? Like, where would you use Vello instead of some other 2D rendering engine? And so the real motivation for us is that it's a basis for what's now an experimental UI toolkit called Xylem. And I'll give a little bit of a demo. The Xylem part is in a very early state. It's still an early rough prototype. But I think using a high performance 2D drawing engine gives you a lot of potential there. And I think Xylem is going to be especially good for applications that have rich graphical content, graphical editors, CAD, scientific visualizations, things like that. Not simple forms, but where you really have a lot of data that has maybe a lot of visual richness to it. Another use case is doing animations in a vector format, so that we have a crate that does Lottie animations. I'll go into the demos and do a quick demo of that now, just to give you a flavor of what this can do. So this is a simple vector animation. So it's built in the Lottie app, and that generates a Lottie file, and then we have Rust code that's interpreting that and drawing it with Vello. And it's running at 50 frames a second. I thought it would be 60, but I guess it's 50 here. But that's because VSync was on. And let's see, there's some throttling that's happening, because I saw it. I don't know what's going on here. That it was okay. There's some throttling that's still going on. But I'll show you a different way to scale the performance. So this is, you can see the N in the terminal, the 128 instances of the animation. And you can see it's not just, they're all offset by time. So this is all completely dynamic. If we had an animation file that was, that was not just copies, you'd still do it. So up to 256 instances, and it's still, completely 100 frames a second with the VSync turned off. I'll show you, let's see, what's one of my other favorite ones? Music. Let's see, workplace is a good one. So, the same thing that, we can do basically, for some reason it's throttled at 100. So if you want to find me afterwards and look at it on the laptop has 120 frames a second. Okay. So that's showing you vector animations. That's showing you one of the use cases for this. And then also games, right? And we'll see a little bit of a demo of that as well. That most games these days are 3D, but if you have a very 2D, a game that fits in 2D and has rich graphics, then Vello would really be an ideal engine for drawing that. All right, so let me go a little bit into the techno. This won't be a hugely technical talk. Just kind of a flavor. Like there's kind of each of these slides could be an hour-long talk. So one of the problems, if your GPU is that fast, if you have that much dynamic vector data that you're rendering, then getting the scene data from the CPU into the GPU to render is more likely to be the bottleneck than the GPU rendering the data. And so one of the traditional way that 2D drawing APIs is written is that you have a render context and you pass in and mute reference to that render context, and that really forces you to do all of your work on a single thread, and that can be a real bottleneck. So we, in our design, we have this, a scene is just a very simple value type, and all of the threads can create scene fragments, which are different parts of the ultimate scene that you want to render, and then those can be combined together in a very lightweight, efficient process, and then that's what gets uploaded to the GPU. So we want to support both retained and dynamic data. In a UI, a lot of the data that you're drawing is the same from frame to frame, and so you don't want to re-encode that. You don't want to have a render context where you're calling the same drawing operations over and over again. You want to encode that into a scene fragment and then retain that scene fragment and then combine it with the dynamic data, so you're able to mix the static and dynamic in the same image that's going to get rendered. So it needs to be simple, it needs to be fast to encode. You don't want to do a lot of pre-processing, because if you do that, that will be your rendering bottleneck. And then when it gets to the GPU, you have to be able to decode it in parallel, because the GPU is a highly parallel computer. I mentioned the multi-threading. You want to be able to create the fragments in multiple threads. And you want it to be a small, compact format. You don't want to expand it out. And so when we have the encoded scenes, they're usually the same size or even smaller than like an SVG that they're decoded from. So we have the scene fragment idea, and you can build them. It's just a value type, so you just create it, and you can do it on threads, you can retain them, and then the primitive to stitch them together is append with transform. So once you have something encoded, you can draw it with any transform. And then there's a very fancy variable length path encoding, so the coordinates can be either 16-bit integers or 32-bit floats. The integers are very good for fonts. And then there's kind of technical details. I won't go into too much detail tonight. But there's this concept of a path tag, which is a 1-byte tag. So if you're encoding this scene that has 8 path segments in it, some are lines, 2 are curves, then the tag tells you which are the lines, and it also tells you when is the end of the path. So it's a little bit like if you're familiar with PostScript PDF, then you'll see like move to, line 2, close path. Very similar, but we just go in with line 2, and then we have an end bit at the end that says this is the end of the path. And the cool thing about this is that directly from the path tag, you can infer a size, which is the number of coordinates that are needed. And then if you do a prefix sum operation, which is a kind of a very GPU friendly, there's work efficient parallel algorithms for computing prefix sum, then that tells you the index. So you can process all of the path segments of the scene completely in parallel. You do this scan to give you the indices, and then when you're decoding the path segments, then you're doing this 100% in parallel. And then the encoding is broken into multiple streams. So take a simple use case that you'll often have, that you'll have a user interface. The user interface has like a scrolling viewport. So the viewport is represented by a clip node. So there's like, already you're seeing there's like tree structure to this scene. So there's a clip node, and then the child of the clip node has a transform, and then all of the contents that you're scrolling are under that transform. And then when you scroll, you just change the translation. Or if you want to zoom, you can do that too. It can do any affine transformation. And so it encodes those into multiple streams. So the transforms are just in their own streams. There's one stream for the path data, there's another stream for the draw objects, and the draw object stream is incidentally where the tree structure is encoded, that when you have this child relationship where all of the things in B are children of the clip node, the way that's encoded is that you have a clip begin, and then you have the contents B, and then you have the clip end. And then the transforms are in their own stream. So if you want to scroll the data, all you need to do is just recompute those transforms in the transform stream, and you can keep the rest. So again, the idea is to offload all of this work off of the CPU, so then when the GPU is drawing it, it applies those transforms dynamically. So another thing, again, this could easily be an hour-long talk by itself, is that in any 2D API, a huge part of what you're drawing is text, is fonts. And so this is still in flight. There's a lot of stuff that's kind of in prototype form, but if you look at the lowest layer, which is loading the outlines from a font, and that includes variable font parameters. So you might have a font that can vary its width, its weight, maybe a lot of parameters. And so all of that code, you have to load that out of the font file and generate outlines for it that are then suitable for rendering. And so first of all, we have a glyph run API so that we don't want to force you to use a particular text layout. So we're doing some of our own text layout, a crate called Parley, which is still very much in early prototype form, but has some interesting capabilities. And we also have a demo where we integrate with Cosmic Text. But the lowest level, the font loading, there is new work being done by the Google Fonts team called Fontations, and the link is there, and I'll tell you later how you can get to the slides. The slides are public now. And this lower level is actually in Chrome Canary. Like if you go to Chrome Canary and turn on a flag, then you will have 100% Rust font loading replacing free type, replacing unsafe C, C++ code that does the font loading. And so another huge part of the motivation for this is that you can do variable fonts with parameters, and you can animate those parameters. So as demo, I might as well just go into that demo right now, and I'll go into there's like a whole bunch of test scenes. So I'll kind of switch back to the text when we get to that. And so these are engineering. This is not beautiful art, but we always start with the GhostScript Tiger. That's always the first thing that you render in a 2D API. And of course, you can zoom in, zoom out, rotate, all these things. So that's just telling you that it works. And then there's there's all kinds of, each one of these things is here to show off or maybe exercise problems in a domain in a part of the problem. And so what you're seeing here is the stroke expansion, and in particular, the stroke styles. So we're applying caps, joins, dashes, and all of the stroke expansion is being done on the GPU, and this is brand new work. Before we had a distance field renderer that could only do round, it couldn't do all the styles, we didn't have dashing wired up, and so now all of that works. And so that's GPU processing, and I can tell you that when I'm talking about clever algorithms, like what you need to do to get all the stroke styles rendered on GPU is really quite interesting. These are just parts of the imaging model. There's non-zero and even odd winding number. Here's another test that sort of exercises lots and lots of strokes. And then here's a demo. It's showing a bunch of things. It's showing the image, but it's also showing a very smooth animation where we have a variable font, and we're dynamically varying both the weight and the width of that, and we're rendering that completely from scratch every frame. And that would be challenging with a kind of a traditional 2D. Most 2D graphics engines you would run into performance problems. There's gradients, all the different kind of edge cases on gradients. There's all of the classic blend modes, your exclusions and hard lights and soft lights and so on and so forth. This is an interesting set of tests. I'm going to talk about this a little later, but these are artifacts that we call conflation artifacts that are basically just the way that the anti-aliasing is computed. And so we have two different methods that if you see the anti-aliasing method that we have selected by default is analytic area, and that's very nice, it's very smooth, it's very fast, but it creates these conflation artifacts. So if we switch to multi-sampled, then those artifacts go away. And so we give a choice of anti-aliasing techniques. And this is another example. I don't know how, yeah, you can see it pretty, maybe the people in the back not so much, but there's sort of blobby artifacts when the strokes are joining, and when you switch to a multi-sampled anti-aliasing mode, that goes away. These are sort of engineering tests for various different things. Obviously, we're stressing the stroke, like does it work when you have a very, very large number of strokes? And the answer is yes. And then this is another, this is a great test. So this is an adaptation of the standard motion mark test, which is a standard test used in browsers to test the speed of the vector graphics drawing, and we can now change the number of strokes, and we go up to, like, this isn't even stressing. Let's see, VSync on, VSync off. Yeah, okay, so it's 120 frames a second with 70,000 path elements. It's pretty good. All right, so those are engineering demos. And one of those that I wanted particularly to show off was the variable font loading, which, that's kind of what this is unlocking, is you don't have to worry about the performance characteristics. So this is built on WGPU. All the code that you're seeing is running on top of WGPU. That's an amazing, like that was mentioned in the last talk, that Deno is also working on that. So it's a real community effort. There's a very broad base of people that are working on this for a lot of different reasons. So obviously, if you're shipping WebGPU in a web browser, then you want that. There's also a huge amount of energy going on in this space with Bevy, game engine, and other game engines, not just Bevy. There's a lot of games that are being written on WGPU. And when we're doing the integration, there's really two directions that this can go. That one is that we can produce textures that then kind of flow into Bevy 3D rendering. And then the other direction, which we haven't done yet, is that you kind of have like a window, a Bevy window inside a UI. And so you're taking those textures from the 3D world and compositing them into the 2D world. Let's see, I don't know, should I do the demo? Let me just do the demo now. I've got way too many demos, but there's just so much that's exciting to show. So this is an integration that just happened like a week and a half ago or something like that. And I'll do the game. And so what you're seeing here is an integration really between three pieces of software. The size is, you don't see the bottom of it. The resolution changed. I don't know what to do about that. But you could, so the spaceship at the bottom, you don't see. The other things are there. But you're seeing three pieces of software being integrated here. So you're seeing Bevy game engine. You're seeing Rive animation playback, and that's actually C++ code that's being wrapped here. And then that's kind of parsing the animation and applying the animation, parameters. And then that's flowing into Vello for the rendering, and then those textures are going back to the game engine. So let me see. I want to show one of the other examples. We'll do 3D HUD. That's fun, and you can just go to the repo and clone it and run it on your own machine, and that's fun stuff. So this is showing, again, like you can see the 3D-ness here, and you can see that the way that the interaction is wired up. And so these are all 2D graphics that are being rendered in Vello and then going into the Bevy rendering pipeline. So again, like the fact that there's this vibrant, like active WGPU ecosystem that we're part of, I think is one of the things that really has me excited about the potential for this project. So for people that do graphics on a GPU, we have a very unusual architecture. It's a pipeline of compute shaders. It's not, most of the time you expect to see a lot of triangles, and there's a vertex shader and a fragment shader, and none of that exists here. It's all compute shaders. And the reason why we've chosen this architecture is that the compute shader in a GPU is this incredibly powerful parallel computer. It has about 10 times the throughput as your CPU. And you can measure that in terms of, pixels per second, or, amount of energy that it requires that it takes to render the same scene. And so how do you unlock that? How do you do these complex 2D, you have to do all this computational geometry to figure out the strokes and the styles and all this other stuff. There's a lot of math. And the way that you do that is compute shaders. And compute shaders, it's powerful, it's exciting, but it's also really hard. Like it's super, and then making it portable, like writing code that runs on one GPU is one thing, but then I want to run that on Macs that have Metal under the hood, and Windows, it's direct 3D. It's an extremely difficult environment. So again, we're building everything on top of WebGPU. So this is all vanilla WebGPU 1.0. We're not doing any kind of weird extensions or anything like that. And this is a much more solid foundation because that's portable. There's a spec. There's increasingly going to be tools, like there's a Wixel analyzer that gives you language server. And just like even that alone, just seeing the red squiggle when you type something wrong is a huge improvement over like compute shaders, GPU programming in general is in pretty poor state. So this is just a sort of a very high level idea of the pipeline of how things flow through the system, that there's this input processing, which is where like the stroke expansion happens and all, the transforms and all that other stuff. And so the idea is that in the input processing, each input element in the scene is being done in parallel. So there's this huge parallelism by draw object. And so that's outputting the brushes, it's outputting the lines after all the transforms, and it's outputting bounding boxes. And the bounding boxes, there's this kind of shuffling or sorting operation that's happening where it's assigning, like, so that every tile, it's ultimately going to be dividing the scene into these 16 by 16 pixel tiles. And so as it goes through the pipeline, every tile knows which draw objects it's going to be drawing, and it generates what's called a per tile command list, which is really kind of an interpreted, it's almost like a bytecode. It says, draw this path, do this gradient, composite, do this blending operation, and at the end you get a 16 by 16 tile of pixels. And then there's this segment sort, which is kind of the magic that makes it all work. And so everything comes together, and then at the end stage, when you're doing fine rasterization, then it's parallel by pixel. So it's like at each stage, you need to preserve the fact that everything is fully in parallel, but there's this gradual shuffling from draw objects on the input to tiles, a completely spatial subdivision on the output. So I gave you a little bit of the demo of the multi-sampled path rendering. This is new work. There's a lot of stuff that's the stroke expansion. These are PRs that are still being reviewed. So you're seeing very fresh, very, very new work. And then multi-sampled rendering, path rendering is really one of the main things I've been working on in the last few months. And again, the goal is, this is a zoomed in view of the conflation artifacts. And this is really a requirement for like Chrome experimented with doing area-based anti-aliasing, and then they had to essentially revert that because people reported the conflation artifacts, and so it's like we can't do that. We have to do higher quality rendering. So that's new work. And here you can see just a little bit of this is sort of test image from internal tool that I use. And you can see a little bit of the hierarchical structure, that there's a 16 by 16 tile, and then within the tile there's pixels, and then within the pixel there's sub-samples. And it actually has to compute the winding number of each sample. So you can really think of this as computing a huge number of winding numbers, and then applying the even-odd or the non-zero rule, and then anti-aliasing based on that. The other thing that I've been working on, and this really has just come together, it's also still in flight, is a technique for doing the stroke expansion, which is based on Euler spirals. So you start with a cubic Bezier, and it subdivides it into these the colored segments. Each one of those is an Euler spiral, and then it's capable of calculating the offset curve, which is a very complicated mathematical operation based on that. And so this is what you're going to see next is not actually Vello doing the rendering, but I think it's very interesting. It's a little Rust tool that is written in the Xylem reactive framework. So this is all related to the UI work, and it's generating SVG, which is going to be rendered in the browser. And so you can see that tool that I was showing you the static image of, that this is an interactive tool, and you can play with this, and you can see, like, you can generate these cusps, you can generate sort of complex scenarios, you can have it kind of flip from one to the other, and you can just see from the way that the points are responding that this is an extremely efficient division, that if you do it too few dots, then you get errors, you get rough output. And if you do too many, then it slows down. It's not efficient. So there's a little live coding thing that I was going to do, but I think we're maybe a little bit short on time. So find me after, and I'll be happy to show you, where I was going to show that if I edited the file and made a change to it, that the trunk tool would recompile it in about 200 milliseconds and then reload it in the browser. And so it's a very fast, like people say like Rust is not good for exploratory programming, for just doing experiments. You want to do that in JavaScript or Python or something like that. And it's like, I would rather write this in Rust and have this fast cycle than using like a Jupyter notebook. That feels clunkier to me. But maybe that's just sort of my personal bias. All right, will this restart from the beginning? No, I'm at the right place. So this is new work, and so this is like I think this is a theme that a lot of the work is solving very hard problems, and that's why it's taking so long. But I think also very interesting directions. Like once this is solved, then I think we'll have a really solid piece of infrastructure for the whole community. And speaking of ecosystem, like this is a list, like we have not shipped a 0.1 crate yet. And so maybe a little bit of a indication of how much excitement there is, how much demand there is for high performance 2D rendering, that these are the integrations that are happening. And so you've already seen the Raph Levien integration demo. And then the, a lot of the motivation for the work is that we want to get this, we want to ship this, we want to get this in production. And the path that, it's still experimental, none of this is shipping yet, but the path that we want to take to get there is to get this integrated into Skia, to have this as at least one of the path rendering backends or engines or whatever within Skia. And so that's in the source code. There is a Skia Vello integration in the Skia source tree, but it is not yet, hopefully soon, outside that experimental framework. There's some game work that's being done. So there's this Vong game by Spencer Imblo. There's other UI work. I didn't even list the Xylem stuff as an external integration, but there's another renderer, which is a native UI renderer for Dioxys, which is using Vello to do the drawing. And then where's Lucas? I saw, Lucas, yes. Mentioned that he's working on an application called Hello Paint, which is being rewritten in Rust. And it's primarily a raster image tool, but like there's a vector layer for drawing like the UI overlay, and that's Vello. And then the GPU, like all of the work is being done on the GPU in shaders. And so the CPU side is not very complex. And there's at least 3 projects out there that have taken those shaders and adapted them. And so FetSim, which is a kind of a educational scientific project, is written in pure JavaScript and runs all the shaders in JavaScript. There's the Go, the GOUI written in Go, same story, where they take the shaders, run them in Go. And there's also, I don't have the details yet, but there's a project by Traverse Research. I believe they're using it mostly for their loading screen, but but they've found that this is a good solution as well. So we don't yet have an 0.1 release. There's more. We want to get it right. There's like none of the demos that I showed so far showed the little flickering artifacts or the thing, flickering in and out. But it's not too hard to provoke that, and that's just robustness work. We actually understand pretty well what needs to happen, but we need to do that, and we want to do that before the 0.1 release. And then we want to do more write-ups, more documentation. There's a lot of features that we want to add. We want to add image filters. We want to do glyphing and caching so that you get much higher performance in a UI. And then in order to get really good performance when you're rendering images, we need descriptor indexing, and we have to work with the WGPU team to get that, because that would be an extension to vanilla WebGPU. So there's always a get involved page, and it always has the links to the things, but I want to call out, like, we have this Zulip chat is a real place where people come together and share expertise in vector graphics, in UI, and there aren't enough good community spaces. If you look at social media, social media is under so much stress these days, and there's so much noise and so much unfriendly behavior. And so we're really carefully curating this, and we don't we don't advertise this super widely, but to the people in this room, like, you know, if you want to get involved in this project, then the place to go is the GPU stream under the Xi Zulip chat. And, you know, there's a lot of really interesting discussions there. And so please get involved. Like, we want to be welcoming. And then we also run, again, not very widely advertised, but every week we have office hours, and we have, you know, a fairly, you know, people share status on projects that they're working on within this kind of larger ecosystem. And, you know, decisions like, what do we do next? How do we solve some of these difficult problems? And so we've been doing that for almost, for just a little tiny bit over a year. And so I've really been enjoying those discussions. So that's the talk that I have. I think maybe we do have time for some questions.
Yeah, we got 5 minutes. So questions?
Thank you. Very, very cool talk. Very interesting. I'm intrigued where the 16 by 16 tile, or where the number 16 comes from for that 16 by 16 tile that the GPU processes.
Great question. So it's pretty standard. Like, so this builds on work. Like, the real foundational work that this builds on is something called CUDA raster, which was done a little over 10 years ago by researchers at NVIDIA. And that also had the kind of 16 by 16 tile structure. And it also had a very similar pipeline where you do like element processing and binning, and you go from elements. That structure is not new to this. It's kind of really adapted from CUDA raster. And the reason for it is that when you do work on a GPU, there's this very natural granularity called a work group. And so a work group is a set of threads that are able to coordinate with each other very inexpensively. So if the threads within a work group need to communicate with each other, it's super fast. And if the threads between work groups need to communicate with each other, it's kind of a nightmare. And so WebGPU, there's some GPUs that will do like 1,000 threads, but the WebGPU says the baseline requirement is that there's 256 threads. And so then that kind of, everything sort of follows from there. It's like the natural granularity of making work scheduled on a GPU.
Great, thank you. And like a slight tack-on question to that would be the anti-aliasing like passes that are done. Are they done like somehow bounded to those individual tiles, or is that just done on the final like
no,
image output?
It's done within a tile. Yep. And so it's actually, there are multiple stages. So like you have to prepare it. You have to do like clipping operations of the lines to get into the tile. But then when it's in the tile, it's rendered. And I should also add, this is a good time to add, that it's all done using compute. So it isn't dependent on the MSAA of the hardware. And so this Mac has a limit of 4x multisampling. And so if you drove triangles in hardware, you couldn't exceed that. But because we're doing it in compute, we can do 8x, 16x, no problem.
Yeah, great, thank you.
Questions?
Hey, great talk. Thanks very much. So we've been thinking about adding a sort of canvas implementation to Dino. Is this something that could power that? Like we've previously thought about using Skia for this, but like pulling in a whole other WebGPU backend is sort of unlikely. And then sort of related question, does this mean that you don't actually have to use WGPU, but you said that this is used in Chromium. Does that mean you could have it like Dawn as your GPU backend for this?
Oh, I even forgot the demo. Whoa, the most important demo. So, so whether you can do it in Dawn, this will answer that question because this is just Chrome running the same code, running the same demo. And then the answer to the first question, not to go on too long, is yes.
Okay. Great.
Last one, if it's very fast.
It's 7 demos.
Thank you, great talk. Do you feel like you're missing out on modern API features? Because WebGPU is kind of stuck. It's like a modern GPU API from 8 years ago, right? It's missing work graph, it's missing bindless, it's missing a lot of stuff. Like,
Mhm.
do you think you'd need it, or you still think that benefits outweigh everything else?
It's a great question. So this is, first of all, this is a very active area, and like, so we pushed to get certain features in WebGPU, like for example, workgroup uniform load, and so that's in there because we needed it. And so the same, I think, is true. Well, a lot of people want bindless. It's not just me, but like that's part of the motivation. So that stuff is going to get added. A lot, the stuff that we desperately need will get added to WebGPU. But part of it is like we work with that constraint, and so like there's a lot of extreme detail. But like, do you do a single pass prefix sum, or you do multi-pass dispatches? And it turns out because of those limitations that you can't do single pass in WebGPU today. Maybe there will be an extension that will let us do that. And so we work around that, and then we kind of discover, yeah, you know, you can tune for this world. Like if you adopt those constraints and you say, what is the best that we can do within those constraints, it turns out to still be pretty good.
Thank you.
Raph Levien, people! Thank you, Raph.
Thank you.
Okay, now we got the last event, which is right now. It's called Bye Bye Goofers and Rustaceans, and it's downstairs. And then goodbye. Thank you for being here.